Okay. Mixed strategy. Example 1. Reduce the following game using the dominance rules and determine the game value. The matrix shows that there are 4 strategies for player A and 4 strategies for player B. By checking the system of domination, we found that R2, the values of R2 is more than the values of R1. Looking at the row 2, you will notice that 3 equal 3, 4 more than 1, 3, 4 more than 3, 2 more than 1, 4 equal 4, and 0 equal 0. So the rule states that if the values of row more or equal the values of other row, the largest row will dominate the lowest row. Then in this case R1 is dominated by R3. Therefore R1 will be eliminated. Now the new matrix expresses 3 strategies for player A and still 4 strategies for player B. Okay. Now let us check the dominance of the columns. Column 3, C3 is less or equal C1. Is less or equal C1. Then C1 will be eliminated. D1 will be eliminated because the values of C3 is less than the values of C1. So C1 will be kicked out. The remaining matrix consists of 3 strategies now for B and 3 strategies for player A. In the next slide, we will continue the solution of this matrix. Okay, the previous matrix shows that there is no dominance of rows or columns. Usually in these cases we will apply the averaging methods. Easier to find the average of two columns or two rows to compare with other column or row for the pair bus of dominance. Okay, referring to the last matrix, the average of C2, T3 and C4 is 2 plus 4. C2 is 2 plus 4 over 2 equals 3. 2 plus 4 6 over 2 3. 4 plus 0 over 2 equal 2, and 0 plus 8 over 2 equal 4. 3, 2 and 4 is known as the values of average column. Now we will assume that this column, the average column, consists of these three values, 3, 2 and 4. Now let us compare these three values, the average values, with the column C1. We found that the average value or the average column has less values than C1. According to the dominance rule, C1 will be deleted. Now the matrix had the shape below. It consists of 3 rows and 2 columns. Again, no dominance, and because the application of the mixed strategy requires 2 by 2 matrix, we will try to delete one of the rows using again the average methods. Now the average of R2 and R3 is 4 plus 0 over 2 equal 2, and 0 plus 8 over 2 equal 4. So the values or the cells of this row 2 and 4. So the average value is more than R1. Then R1 will be deleted. The remain is R2 and R3. Okay. Now the last stage or the last step, so we can apply the odd means tools, because this odd means require 2 by 2 matrix. Now as first we will apply the row odd means. The odd means for R1 equals the difference between the value of R2 8 minus 0 equal 8, and the odd means of R2 equal the difference between the value of R1, 4 minus 0 equal 4. Then we will find P1, the probability. P1 equal 8 odd means over the summation of two odd means, 8 plus 4. 8 over 8 plus 4 equal 8 over 12 equal 2 over 3, and P2 equal the odd means 4 over the summation of two odd means, 4 over 8 plus 4, 4 over 12 equal 1/3. The columns odd means the odd means of C1 equals the difference of C2, 8 minus 0 equal 8, and the odd means of C2 equal the difference of C1, 4 minus 0 equal 4. Q1 equal 8 plus 8 over 8 plus 4, 8 over 12 equal 2 over 3, and Q2 equal 4 over 8 plus 4, 4 over 12 equal 30. Now we will use one method to find the game value. 9 equal 4 times, just look to the column C1, 4 times 8 between brackets plus 0 times 4 over all this over 8 plus 4 equal 32 over 12 equal 8 over 3. Then 8 over 3 is game value. Optimal strategy for player A is, just look, player A has 2 over 3 and third. 2 over 3 third 0 0. For player B he has 2 over 3 and third. 2 over 3 third 0 0. This is the end of mixed strategy. Mixed strategy, if it require dominant or odd means method, the odd means method requires 2 by 2 matrix. Example 2. Determine the optimum strategy and values of the game whose payoff matrix is shown below. First, there is no saddle point. If there is a saddle point, this matrix can be solved by pure strategy. Once this matrix has no saddle point, we can apply a mixed strategy. And because the mixed strategy or odd means method requires 2 by 2 matrix, so the requirements are satisfied to use the odd means to determine the optimal strategy using mixed strategy. This matrix or this game has, each player has 2 strategy, because this matrix consists of 2 columns and 2 rows. First, let's apply the R odd means. Odd means R1 equal the difference between the values of R2 equal 1 or 4 minus 3. Odd means R2 equal the difference between the values of R1 equal 3 or 5 minus 2 equal 3. P1 equal 1 over 1 plus 3. 1 is the odd means. 1 plus 3 is the summation of 2 odd means equal 1 over 4 quarter. P2 equal odd means 3 over 1 plus 3, 3 over 4. These two probabilities for player A. For player B or column odd means, the difference, the odd means of C1 equals the difference between the value of C2. 4 minus 2 equal 2, and the odd means of C2 equal the difference between the values of C1. 5 minus 3 equal 2. Then Q1 equal 2 over 2 plus 2 equal half, and Q2 equal 2 over 2 plus 2 equal half. Now the game values equal 5 times 1 plus 3 times 3 over 1 plus 3 equal 14 over 4 or 7 over 2. This is the game value. Player A strategy is 1 over 4, it's P1 and P2, 1 over 4 and 3 over 4. The B strategy is Q1 and Q2, half and half. Averaging example 1. Given the following matrix, determine the game value and optimal strategy. Sorry, this is not averaging example. This is next strategy. So two strategies for each player. Player A faces two strategies, as well as player B faces two strategies. The usual steps. Step 1, to find the oddments, then find B1 and B2. Next, column oddments, and then Q1 and Q2. Third is to find game value, and the last step is to find the optimal, how to determine the optimal strategy. Now let's apply for raw oddments. Oddments R1 equal 0, negative 0, 0, negative negative 1 equal 1, and 2, negative negative 1 equal 3. We will try. The oddments to be positive. So the two oddments are 1 for R1 and 3 for R2. P1 equal 1 over 1 plus 3 equal quarter, and P2 equal 3 over 4. Moving to the column oddments, oddments C1 equal 0 minus 1 equal 1, and oddment C2 equal 2 minus 1 equal 3. Q1 equal 1 over 1 plus 3 equal 1 over 4. Q2 equal 3 over 1 plus 3 equal 3 over 4. The game value is 2 times 1 plus negative 3 times negative 1 times 3 over 1 plus 3, no, 1 over 4. Optimal strategy is 1 over 4, 3 over 4 for player A, and quarter 3 over 4 for player B. We will try also this to determine the optimal strategy. Nash equilibrium. The Nash equilibrium was introduced by American mathematician John Forbes Nash in 1950. It refers to an optimal state where the game considered stable and no actor can change his strategy. Nash equilibrium is a game theory concept that determines the optimal solution in a non-cooperative game in which each player lacks any incentive to change in his initial strategy. Under the Nash equilibrium, a player doesn't gain anything from deviating from initially chosen strategy, assuming the other players also keep their strategies unchanged. Example: imagine two competing companies, Company A and Company B. Both want to determine whether they should launch a new advertising campaign for their products. If both companies start advertising, each company will attract 100 new customers. If only one company decides to advertise, it will attract 200 new customers, while the other company will not attract any new customers. If both companies decide not to advertise, neither company will engage new customers. The payoffs of this matrix as below. This is the matrix about which the previous slide stated. Company A should advertise because the strategy provides a better payoffs than the option of not advertising. The same situation exists for Company B. Thus, the scenario when both companies, Samsung and Apple, advertise their product is Nash equilibrium. When both companies advertise their product. Okay, this is known as Nash equilibrium. The Nash equilibrium is an optimal state of the game where each opponent makes optimal moves while considering the other player's optimal strategy. Both terms are similar but slightly different. Nash equilibrium states that nothing is gained if any of the players change their strategy while all of the other players maintain. Dominant strategy is a situation when the player will select his best possible option, no matter what does his rival player do. Okay. Nash equilibrium. New look. Find the pure strategy of Nash equilibrium in the following game, in which player 1 had 3 strategies T, M and P, while player 2 had 3 strategies L, C and R. The matrix is shown as below. Now let us arrange the impact of the choices of player 1 on the choices of player 2. If player 1 chooses strategy of T, so the strategy of T in the first row, so then player 2 will take the highest outcome. Now the strategy now is focusing on row T. If player 1 chooses T strategy, let us see what the reaction of player 2. Player 2 will choose the highest outcome in the T row. The highest outcome for player 2 is 2, R2 in the column R. Okay. Let us move to the second choice of player 1. If player 1 chooses strategy of M, let's move to the M row. If player 1 chooses M strategy, then player 2 will look for the highest outcome in this row. The highest outcome for player 2 is 4. It is under the L column. It is under the L column. Okay. Now, if player 1 chooses strategy of B, then player B will choose strategy of L, because column L gives player 2 the highest outcome equal 3. Okay, that's finished for player 1. Let's move to the strategy or the campaign of player 2. If player 2 selects strategy of L, the first column, the strategy of the first column, if player 2 chooses L, then player A also will choose the highest outcome 3, or he will choose M strategy. If player 2 chooses C strategy, then player A will look for the highest outcome equal M and T. If player 2 selects R strategy, in R strategy, player 1 either selects 4, 2 or 3, but the best outcome is 4. The above strategies shows that the common cell between the two players are 4, 2 and 3, 4. 4, 2 means strategy T, a combination of strategy T and strategy R. The next combination is 3 and 4. This combination means strategy M and strategy L. This matrix shows that Nash equilibrium has two options, TR and ML, or 4, 2 and 3, 4. Again, Nash equilibrium. Consider the following matrix, which describes the respective strategies and the corresponding payoffs of El Razi University EU and Sudan International University SIU. Referring to that matrix, which of the following statement is true for the matrix? El Razi University has no dominant strategy. Sudan International University also has no dominant strategy. The game has Nash equilibrium. Neither El Razi University nor Sudan International University has dominant strategy. So we will use the given matrix to answer the given 4 questions. Of course, if one of them has no dominant strategy, or if the two universities has no dominant strategy. Question 4 will be illuminated. So if Sudan University chooses advertise, then Al-Razi will take advertise because it gives highest outcome equal 11. If Sudan University chooses don't advertise, then El-Razi University will select 20 or don't advertise equal 20. So don't advertise, El-Razi will take 20. Since EU has different strategies, therefore has no dominance strategy. Now, if El-Razi University chooses advertise, since Sudan University will take don't advertise, equal 9. If EU chooses don't advertise, this SIU will select advertise equals 6. Since SIU has different strategies, therefore has no dominance. The Nash equilibrium is to advertise for both of them, or 11 and 6. Multi-Nash equilibrium. Amanda and Iman are registering for the new semester. They both have the option to choose either a French language course or a German language course. They have only 1 hour to decide and have no time to communicate with each other. If they register for the same class, they will benefit from the opportunity to study for the exam together. However, if they choose different classes, neither of them will get any benefit. The matrix shows multi-Nash equilibria. If Amanda and Iman register for the same, they will benefit from studying both for the exam. Thus the outcomes French and German. So if Amanda choose French, Iman will also choose French. If Iman choose French, Amanda will also choose French. If Amanda choose German, Iman will also choose German. If Iman choose German, Amanda will also choose German. So the underlying is outcomes either French or German. prisoner's dilemma. A prisoner's dilemma is a situation where individual decision makers always have incentive to choose in a way that creates a less than optimal outcome for individual as a group. If it occurs in many aspects of economics. The prisoner's dilemma is a paradox in decision analysis in which two individuals acting in their own self-interest don't produce the optimal outcome. The prisoner's dilemma was developed in 1950 by Rand Corporation mathematician Merrill Flood and Melvin Treasure during the Cold War, but later given its name by the theorist Alvin Toker. Today, the prisoner's dilemma is a paradigmatic example of how strategic thinking between individuals can lead to suboptimal for both players. Key points of prisoner's dilemma. A prisoner's dilemma is a situation where individual decision makers always have an incentive to choose in a way that creates a less than optimal outcome for the individuals as a group. The prisoner's dilemmas occur in many aspects of the economy. In the classic prisoner's dilemma, individuals receive the greatest payoffs if they betray the group rather than cooperate. If games are repeated, it is possible for each player to devise a strategy that rewards cooperation. People have developed many methods of overcoming prisoners' dilemmas to choose better collective results despite apparently unfavorable individual incentives. Understanding the prisoner's dilemma. A typical prisoner's dilemma is set up in which a way that both parties choose to protect themselves at the expense of the other participants. As a result, both participants find themselves in a worse state than if they had cooperated with each other in the decision-making process. The classical example: two prisoners are accused of a crime. Each of them has two choices: either to confess or to deny in response to the guarantee given by the police authorities. If both deny about the crime, the both get jailed for 2 years each. If both confess that you both did the crime, you get 1 year, whereas the other get 10 years jail. If you deny and partner confesses, you get 10 years and partner get 1 year. If both of you confess, then both of you get 3 years each. The matrix below illustrates the previous options given to the two prisoners. Now, if prisoner 2 chooses confess, then prisoner 1 will choose the least years, 3 years, or confess. If prisoner 2 chooses deny, then prisoner 1 will choose the least scale, 1 year, or deny. If prisoner 1 chooses confess, then player 2 will choose also confess, equal 3 years. If prisoner 1 chooses deny, then player 2 will choose deny also, equal 2 years. The Nash equilibrium is 3-3, that both of them will confess.